Okay. Good afternoon, everyone, and welcome. Before we start, I would like to check, can everybody hear me?
Yeah.
Great. So, once again, welcome everybody to our Supergen Energy Networks Hub webinar series. My name is Dragan Cetenovic, postdoctoral research associate at the University of Manchester, currently working as a part of the core research team of the Supergen Energy Networks Hub. The Hub mission is to establish a vibrant, well-connected, diverse, open, and communicative energy networks community with deeper understanding on whole system approaches to energy networks. And to support this mission, Supergen Hub organizes a series of monthly webinars with a variety of topics regarding different energy sectors. Today's topic is mainly about the initial results from FlexFund Supergen Energy Networks Hub project, titled Using Machine Learning to Represent Power System Dynamics. This will be presented by Panos Papadopoulos, a senior lecturer at the Department of Electronic and Electrical Engineering of the University of Strathclyde. Dr. Panos working in the area of electric power system stability and dynamics. He has received a PhD degree from the Department of Electrical and Computer Engineering at the Aristotle University of Thessaloniki, Greece, followed by a postdoctoral position at the University of Manchester. In 2019, he has been awarded a prestigious £1.2 million UK Research and Innovation Future Leaders Fellowship on addressing the complexity of future power system dynamic behavior. He is also currently the chair of the IEEE UK and Ireland Power and Energy Society chapter committee and a member of IET Engineering Policy Group Scotland. The title of his presentation is Using Machine Learning to Predict the Onset of Blackouts. After the presentation, 10 to 15 minutes will be reserved for Q&As. I would like to invite all attendees to raise the questions at the end of the presentation. Any questions and comments are also welcomed in the chat during the presentation. Also, the session will be recorded and it will be available on the Supergen Energy Networks Hub website. So without further ado, join me in welcoming Dr. Panos Papadopoulos. So Panos, the microphone is now yours.
Thank you. Thanks a lot, Dragan. Hello, everyone. Thank you for the introduction. So probably I don't need to say anything more on the first slide. I'll be talking today about some initial results from Supergen Energy Networks Hub FlexFund project, part of the first round. University of Strathclyde is leading this project, and we have also the Alan Turing Institute as a collaborator, and we have National Grid being an industrial supporter as well. So the main activity of this project, where all the results are mainly coming from, basically, is so-called data study group, which effectively is something that is facilitated by the Alan Turing Institute, and it's a 2-week-long intense challenge where we try to bring together a problem for power engineering from power systems and pose it to the machine learning research community to try to get the best answers basically out of. And I have to say at this point that this is very closely aligned to my UKRI Future Leaders Fellowship as well. So this research area is very active as part of the fellowship as well, of my fellowship as well. This is the team around the setting up the Data Study Group Challenge. We're mostly from the University of Strathclyde. So I'm the project PI. Dimitrios Zelepis is a co-investigator of the project. We had Sofia Koukoura being the Data Study Group Challenge PI, so from the side of the Alan Turing Institute. Georgios Nakas, who is a PhD student working around this research area, so his core research is around this research area. And we also had a summer intern, Alexandra Ligeti, working with us for a month and a half during summer, working on the preparation of the data set and so on. So at this point, I should also thank the Alan Turing Institute. They did a really great job facilitating the data study group and facilitating our challenge. It was particularly challenging this time because of COVID. So the event is usually held in person, but it had to turn online, and they did this fantastically, I have to say. I mean, no one could tell that this is the first time that they are running this online, so a big thanks to them. And a big thanks to the data study group participants that worked on our challenge and formed the team working on our challenge. So Marilyn, Oli, Dom, Josh, Alara, Chloe, and Amar, they did an excellent job, and big thanks goes to them as well. So I'll start by so this will probably take around 25 or 30 minutes, the talk. I'll give a bit of a background around the problem. Most of you might have heard these things, but I'll try to recap it as quickly as I can. And then I'll talk a little bit specifically about the modeling we did and the machine learning part of the prediction problem that we set to during the data study group challenge. So again, most of you might have seen this. So this so-called energy trilemma, a few years ago, or a lot of years ago now, it used to be power system operation and planning used to be mainly about balancing security and affordability, but now sustainability, mainly driven by climate change concerns, is an integral part, and this is effectively translated into bold decarbonization targets set by governments throughout the world. We have such targets set here in the UK, of course, and what practically this means in terms of power system operation is that we are shutting down or decommissioning a lot of the fossil fueled power plants, and we are replacing them with loads of wind generators, solar PVs, electric vehicles as well as part of decarbonizing transport. And there's also a big discussion around potentially electrifying heating to decarbonize it. So that's another aspect of this. And what we are mainly interested as part of this discussion here is that these new additions, these changes in power systems, effectively, in a sentence, I would say that they increase the uncertainty and the complexity of power systems. And we are mainly focusing on system security here, which is about making sure the system is stable and keeping voltages and frequency within normal operating limits. This is particularly challenging task when we consider that all these new devices might introduce different dynamic behavior, and especially it's becoming especially difficult when we are talking about the so-called high impact, low probability events. And I'll be discussing a little bit about that later on. So in general, power systems are dynamic nonlinear systems. Arguably, they are among the most complex man-made systems. And how we represent their dynamic behavior is we describe them using thousands, even more, of differential equations. And normally, one of the main ways that we address this, or we do studies around the dynamic behavior of the system, is we use numerical integration techniques. So we solve these differential equations time step by time step, from timescales ranging from milliseconds up to tens of seconds or even longer than that. And this is a very computationally intensive process. And if we add on top of this the increasing complexity, which to a large extent comes from all these new devices that are being connected into the system, which are mainly power electronic interface. So for example, wind, solar, batteries, HVDC links, electric vehicles, and so on. And they can introduce further strong nonlinearities, such as limiters or discrete control actions, for example, the activation of a fault right through mode and so on. And of course, on top of it, we have the increasing uncertainty as well, which again, to a large extent, comes from the intermittent behavior of the primary energy sources, of some of those sources, for example, wind and solar. And if we wanted to do an exhaustive search of all possible operating conditions and contingencies, this ends up usually being even billions of cases in a real network, in a realistic network. And this is quite difficult to address. So it's becoming increasingly promising to try and predict in close to real time impeding instability. And we do have measurements in modern power systems, and state-of-the-art machine learning techniques have shown promising results that they can tackle this problem. And the option they open up is that you can actually do corrective control actions very fast after impeding instability is predicted. Discussing a little bit in general about stability and security assessment using machine learning, so the background available in the literature, if you will. So stability prediction, which effectively means predicting whether the system is stable or not after a disturbance. So this has been addressed in the literature to a certain extent. Rotor angle stability particularly has been investigated a lot, both transient and small signal, so both of those aspects. And several machine learning methods have been applied to this problem. So starting from decision trees, this was probably one of the earliest adopted techniques. But neural networks have also been used, including convolutional networks and long short-term memory, which we'll be discussing a bit more in detail later on, support vector machines as well, and so on and so on. And the problem of both binary and multi-class classification has been addressed, meaning binary means just predicting whether the system is stable or not, and multi-class is adding a bit more information on that, effectively identifying the unstable groups of generators, basically. Similarly, a lot of those techniques have been applied for voltage stability as well, both for short-term and long-term. And an added thing here was that regression has also been applied to predict the voltage stability margin effectively. So not classification only, but regression as well. Now, moving on to dynamic security assessment. So this has also been heavily addressed by several machine learning techniques. So here the target is to predict whether the system is secure for a set of credible contingencies. So it's slightly different to the problem of stability prediction, if you will. This has been posed commonly as a binary classification problem, so predicting whether the system is secure or insecure. What's up? And there are approaches based on static calculations, so power flows effectively, but also methods that do take into account dynamics as well. And in both stability and dynamic security assessment, there are various challenges that have been addressed related to how you sample the possible search space, how you create a meaningful data set, how you increase the performance of those methods. So a lot of investigation around these aspects has been done, but of course, a lot more remains to be done in the future as well. So what are we doing differently here in this project? So we are effectively trying to predict more complex interactions that are related to multiple dynamic phenomena at the same time. So we're trying to model, in the first instance, combine dynamics related to rotor angles, voltage, frequency, and also discrete actions coming from protection devices. So we are effectively trying to model and predict a cascading failure in a bit more detail. And how we address this as part of this specific project is just predict the onset of a cascading event. So something like a binary classification saying a cascade is about to happen or not. So that's the information we get from the prediction effectively. We tried 3 methods. We'll talk about that a bit more in detail later. And we also did some feature importance analysis to understand how measured variables would help predicting the cascade, a cascade. So just a bit of discussion on what is a cascading failure. It's defined by an IEEE working group as any sequence of independent and dependent outages. So this can be external threats, natural disaster, a storm passing by and knocking down towers or something like that. Or it could be dependent outages, which effectively is violations of operating limits or instability of the system, which triggers some protection devices to disconnect components. And this is what we are actually focusing as part of this study. So only dependent outages is what we are dealing with here. After an initial contingency, I have to say that. effectively, we're talking about sequential disconnection of power system components. Could be generators, lines, loads, a number of components of the power system. Some power system variables may go out of their operating limits, causing a so-called disconnection or a trip. And this can be because a protection device is activated to avoid further damage to equipment, but it also could be due to maloperation or human actions or other reasons as well, which again, we are not tackling as part of this framework. So what is of interest is to understand which component is going to be disconnected for what reason and in what sequence as well. So ideally, we would want this full set of information. Effectively, cascading failures is one of the key mechanisms that lead to blackouts. So this is in general a very complex phenomenon because it involves various timescales, starting from more slow phenomena related to thermal limits of network elements and moving on to long-term and short-term voltage stability, frequency, angular as well. And it's clear from the literature as well that the need to include dynamics is becoming more significant. There are, of course, static approaches based on AC or DC power flows, but there are also dynamic approaches available which are more accurate with the apparent problem that or challenge that they have high computational effort, of course. And what we did here is we tried to pose this as a time series prediction problem to identify whether a cascading event is about to happen or not. So first of all, we needed to model things. So we developed a model that can capture this cascade. We used the RMS framework. So there's a big discussion around whether this is enough in future power systems with a lot of power electronic interface devices, but we just chose to use the RMS framework for now. And we also added protection devices, and we scanned various operating conditions, taking into account the different loading, system loading, and different wind generation, wind penetration, if you will. And we tried to characterize the cascade, something that I will show a bit in more detail later on. So these are the networks we used. We just developed a couple of them, a smaller network, the 9-bus, and a larger, the 39-bus. We modified them. Again, they are both RMS models. We modified them a bit. We added some wind generation and a number of protection devices, as you can see here, and also a number of relevant control mechanisms, which are related to cascading failures. For example, load tap changers or under frequency load setting schemes that are active as part of each one of the loads of the network appearing there. This is an example of how a cascading event ends up looks like in simulation. You can see a couple of figures. One is a voltage, one is a frequency for various parts of the network. And you can see in the table here on the right, I don't know, you probably can see my mouse as well. So this is the detailed events describing the cascade, and we can kind of codify it to look like that on the top, where you can see the different sequences, the different events of the cascade, first, second, third event, and you can see which component trips. So for example, here NSG2 refers to one non-synchronous generation to one wind generator located in a specific area of the network. And then you can also see the reason for tripping, for example, UVs under voltage, or it could be under frequency and so on, under speed and so on. And then what we did is we effectively simulated loads of such cases to cover a large range, or more or less all the possible operating. We tried to capture in a kind of a brute force approach all the possible operating conditions, at least the range of them, by discretizing, of course, and taking certain time steps. And we ended up having a number of around 44,000 cases from different combinations of system loading and wind penetration in different areas and different contingencies happening in different lines of the network as well. So our initiating fault is always a three-phase fault happening on a line. That's the beginning of the simulation, effectively. And we got a number of different cascades. So you can see an example here on the table with the most common of them appearing. And we tried to characterize them a little bit. We did some statistical analysis. So you can see here the number of events and the frequency that they appear. So you tend to have a lot of short events. This is what this first figure shows here. But you tend to have even some events that have a very high number of failures associated with them, or disconnections or protection device activations, if you will. Here is the time of events. So some of them are happening quite fast, but some of them are happening also quite later on in the simulation. And we also try to see what is the percentage of load that's associated with such cascade. Again, we have a large number of them which have a very low loss percentage, but some of them have a very high. Effectively, they can even lead to a full system collapse, basically. And we also try to bulk a little bit the reasons for tripping to understand them a bit better and get some meaningful information out of them. So, for example, how many trips are due to overvoltage, or how many trips are due to pole slip, and so on, in this entire data set. So now moving on a little bit to setting up the challenge itself. So what we did is we took this data set effectively that came out of the simulations of this simulation framework, and we set an aim to try to predict a cascading failure is about to happen slightly before it happens. And the idea is to generally train a machine learning model with simulated time series data, and we can do this offline, having this big data set available, and use it then in real time, utilizing available online measurement data as they would be coming in a realistic case, and then predict a cascade is about to happen or not. We had a more open question, I have to say, here in the beginning. So binary classification ended up being what we could tackle within the short time frame of the 2 weeks that we had. But the question was much more open in the beginning in terms of predicting more informative, predicting things in a bit more informative way. So the idea is that we choose a prediction window, which we chose it to be at least half a second before the first cascade happens. So this is effectively the room that we have to apply some corrective control action before the first cascade eventually happens. And the target is to do a binary classification, as I mentioned before. And we tried initially testing the methods with having available variables, power system variables that would normally be able to be measured by PMUs, like, for example, voltages or frequency or power flows, active and reactive power, but also added some additional state variables. So, for example, speeds of the generators, which wouldn't normally be available from a PMU measurement device. This was more like a test. And then we proceeded to a more realistic case when we did the same thing using only measurements available through typical PMUs. But the results I'll be presenting today are basically from the first bullet point, so with state variables, additional state variables included. I should also mention that this is purely a simulation exercise here, so there are no real measurement involved. It's just purely simulation, both training and testing data sets and so on. So this is how the data looks like. We have this kind of matrix form that you can see here, where you see several parameters. 245 is roughly a number, because sometimes you have a bit more, a bit less, because some wind generator goes online or offline, and so on. But it's time series data you have a number of features that you can use, which are effectively components and different variables related to those components. So it could be the voltage of a bus, the active and reactive power flow of a line, the speed of a machine, and so on. And of course the targets, we talked about that. This is a binary classification. So this is the overview of the methodology that the participants of the data study group came up with. So there was a little bit of pre-processing involved. There needed to be some kind of interpolation because the time steps were different in the original data set. It was downsampled as well to have a more realistic sampling time that would be available in a real setting from PMUs as well. And data needed to be normalized. This is important for the training of the machine learning algorithms. Choice of window was also an important aspect, which I think there needs to be also some future work involved here. And finally, the data were prepared for batches for the training and testing. Then there was the model training and evaluation part, where we tried effectively 3 main types of machine learning models. Logistic regression starting as the easiest, let's say, the simplest solution, moving on to long short-term memory networks, a type of recurrent neural network. And we also tried autoencoders. I'll talk about this again later on. And we also tried feature importance by permutation, where we kind of wanted to get a sense of what is important or what would be important to utilize when we are trying to predict a cascade from happening. And of course, then we tested the trained models. And there was also a bit of discussion around the hyperparameter choice. And of course, we finally have a look at the performance of each one of those models. That's the last slide of the presentation that we will be talking about the performance of the models. So talking a little bit about logistic regression, this is a relatively simple classifier. We used it as a binary classifier. You have the input, which is the features denoted by X here and so on the left-hand side as well. These are all the different variables that I've shown in the previous table. So it could be voltages, frequency from different locations of the network, active reactive power flows, and so on. And then we have the weights, which are effectively multiplied by the input, and these are calculated during the training, coming out of a minimization from a cost function, And this passes through an activation function. Logistic or sigmoid activation function is used in this case. It looks like the small figure here, you can see on the bottom. And the output Y effectively is 1, whether a cascade is predicted, or 0 if a cascade is not predicted. And this is effectively coming through the when the output of the activation function is larger than a threshold, then the output becomes 1, otherwise the output is 0. Moving on to a bit more complicated method, the long short-term memory neural network. So this is a type of recurrent neural network, which are quite useful in processing sequential data or time series data. And the main difference in terms of standard feed-forward neural networks is that they have recurrent connections in the hidden layers that can effectively maintain information from the past, from previous states, and they form a sort of a memory effectively. But typical or standard recurrent neural networks have the problem of the so-called vanishing gradient, which can make it difficult to retain memory for a longer time. So for this reason, basically the long short-term memory neural networks have been developed, which have been shown to be very effective in handling time series data. And they can actually retain memory for longer time now, which is quite useful in our case. And they can also remember over a variable time frame, which again is particularly interesting for this specific problem that we are trying to address, because cascades involve phenomena that span various timescales. So this is a useful feature to have. And you can see here in the figure on the left-hand side as well, this is one cell, effectively, a neuron of the long short-term memory neural network. And it has at the core of it a memory cell, denoted by CT here. And you have also 3 gates, the input, output, and forget gate, which are interacting with this memory cell, and they are managing the flow of information through this cell, effectively. Autoencoders have been tried as well. So you can effectively split this in 2 parts, the encoder and decoder. So the encoder is taking the input and tries to map it to a lower dimensional representational space, as you can see here in the middle, denoted by Y, the red. And the decoder then, taking this as input, tries to reconstruct the input effectively, the original input. So in this, because neural networks are used as part of the encoder and decoder, so you can use LSTM, long short-term memory neural networks, or convolutional layers as well. And how we used it here is we used it as an anomaly detection, where still time series is coming as input, and we try to identify whether an anomaly is happening, which is a cascade in our case. And we tried several variations, including LSTM networks or convolutional networks, or we also tried inputting autoencoder processed data to an LSTM and training a normal LSTM. We'll see how all these methods performed. We also did feature importance using permutation. We did this on the LSTM and logistic regression models. How you effectively do this is you shuffle a single feature and you measure the change in the accuracy. And this is pointing towards whether this feature is important or not. For LSTM, some results are shown here on the figure. And you can see that some of them are actually impacting accuracy negatively, so reducing the accuracy, but some of them are improving the accuracy. And for example, we can see that certain lines here, so certain lines have high change in accuracy. So we can see that these are important features. And also some generator features have shown to decrease the accuracy. So these are specific variables related to generators or specific variables related to specific lines of the network. Similarly, for logistic regression, we did a similar thing, but we could also bulk here the features related to all the lines of the network or all the generators of the network. And we can still see that lines are very important, generators are important, non-synchronous generators, in our case it was wind generators, are also very important as well. So this is giving effectively very interesting insights to understand a bit better the problem and potentially open up the possibility to train models with a reduced number of features in the future. We haven't tried that yet, but this is one of the things to do in the near future. So some initial results coming out of these tests that we made. I think it's interesting first to discuss about how we measure the performance of the models. This is well-known or not confusion matrix, which you can see that in the columns you can see the actual class, predicted class, the actual class, and in the rows you can see the predicted class. And you, in our case, a positive class means a cascade is happening, a negative class means no cascade is happening. And when we have, for example, the actual class being positive and the predicted class being positive, then we have a true positive, which means that the cascade is predicted correctly and it happens as well. Similarly, a true negative is no cascade is predicted and it does not happen. So again, correct prediction. When we go to the mistakes, let's say, that the prediction model does, when we have a false positive, then a cascade is predicted, but it doesn't happen in reality. This is a false positive. And the false negative is when a cascade is predicted, sorry, no cascade is predicted, but it actually happens. So we are missing an actual event. This is quite important, and this is quite, could be a situation where it's actually not good for our prediction model. And based now on this confusion matrix, we can create several metrics. These are standard metrics using classification models. And accuracy, you can use the true positive and true negatives over all the possible cases. And this is a kind of good overview, but at the same time, it can potentially be misleading because we don't know exactly where the mistakes are coming from, whether they are false positive or false negatives effectively. And then we have precision, which counts true positives over true positives and true negatives. And then we have recall, which is quite important for this specific problem because it shows us in a way how the model performs in terms of the false negatives, which we want to avoid. Because a false negative would mean that our predictor, the actual system that would be sitting there and monitoring the performance of the system would say everything is fine, but a cascade would happen eventually. And cascades are quite disruptive events. In the worst case scenario, they can lead to a blackout. So we really want to avoid a false negative in that case. And F1 score is just the mean value effectively of the recall and precision. So having said this now, I think now this makes a bit more sense. These are the actual numbers that we got from the models that we trained. And we can see that logistic regression surprisingly performs quite well. It has a the highest precision and very high accuracy as well, the highest as well, very close to the LSTM, but the highest. And it's also the simplest model, which is quite good and quite welcome in that case. LSTM performs also very well too. It has slightly lower accuracy and precision from compared to the logistic regression, but it has a higher recall, which is quite important as I described in this specific problem. The autoencoder didn't do very well. It had low accuracy, very low recall and F1 score, so didn't perform very well. And the encoder decoder LSTM, so the LSTM using the autoencoder as input, didn't learn anything useful actually. So the performance was quite bad basically. Again, probably a disclaimer here that tuning, maybe choosing different hyperparameters or different features as input might have some room for improvement in this method, so that wouldn't be a definitive, let's say, outcome. Just to sum everything up, so in general, machine learning shows to be quite promising at predicting a cascade is about to happen. So it can effectively capture this complex dynamic behavior from the combined effect of all these different mechanisms, if you will, related to voltage, frequency, and rotor angle stability. We formulated it as a binary classification problem, and we tried several machine learning models, logistic regression, LSTM, and autoencoders mainly. And again, for future work, we also did some feature importance to understand what is significant and not to include in the training process of the models. And for future work, fine-tuning a bit the hyperparameters, trying different models would be really interesting, defining the time window also differently, and the big question of how you generate the data set, I think that also needs to be addressed at some point in the future. Yeah, and this is just some relevant publications for anyone interested in further reading, and my contact details here. And that's me. I'm happy to take any questions you have.
Okay, Panos, thank you very much for this interesting presentation. I will now open the floor for the questions and discussion. I will start first with the questions from the chat. So we have first question from Robin Priest. I will call Robin to read his question. Or
sorry, it took me a while to unmute there. Sorry. Hi, Panos. Yeah, no, I just wanted to ask why do, well, I've stacked a few up, but I'll just go with the first one. Why do the features decrease the accuracy? Why don't they just get weighted to 0 and then have no impact? I'm a bit confused as to why they would still actually kind of pass through the machine learning classifier if they're having a negative impact.
Yeah, that's a very good one. And I was wondering the same thing. I think this has to do with the training process, because this is effectively an optimization problem. So it comes from that. It effectively having more complicated features, if you will, the optimization doesn't work that well. So the model ends up being worse off when you include more features rather than less features. But I would, at least myself, want to understand why this happens or how it happens in more detail a bit better myself. So yeah, I think there's a bit more work to be done here on why this happens.
Okay, cool.
Okay, we have a question from Xin Zhang. I will call Xin Zhang to read his question.
Oh, hello. Hi everyone. Hi, Panos. Really interesting work. Thanks very much. So my question is about the computational time for contingency assessment. Normally my understanding is even for n-1 contingency assessment, it takes a long time to complete. Some contingency analysis, such as voltage or thermal, will be quicker to run, but some of them, like transient or dynamic stability assessment, takes maybe more than 10 minutes to complete. Even for n-1, assessment. I understand you are looking at the cascading trip with about 45,000 simulation. So how quick would your machine learning method be to complete all this simulation? And is that quick enough for a control engineer to take any action before the cascading trip actually happens? Thank you.
Thanks a lot, Zin. Yeah, so this is capturing the essence of probably why it's a good idea to try using machine learning to address this issue. So the idea is that the training of the machine learning, which is based on these thousands of simulations, as you mentioned, is happening offline. So you can do this at any point, right? So these 45,000 cases took a long to run, as you said. So we ran it in a kind of a powerful yet but conventional computer, and it took probably something like 10 days continuous running of simulations. So that takes time, and this is why it's a problem, and you couldn't have done this detailed analysis online. The idea is that you can do it when you have the time at some point, train the neural network, and then the neural network does the classification very, very, very fast. I don't have a number to quote on how long the evaluation takes, but it is, I would expect milliseconds to be. So just to give you an idea, when in similar work involving decision trees to do the actual, to ask the model, is this case stable or not, it took even less than milliseconds, it was microseconds. So you instantaneously got a response out of the model. So the training bit, which is the intensive part, you can do it at any point when you have time. You can run as many simulations as you can offline, train the model, and then online the evaluation is done within, I would expect, milliseconds, basically. So that way we are trying to make sure that the prediction is happening at least half a second before the first cascade, so that you have some time to take a kind of a fast, it has to be automated control action, but it can potentially be done.
Yeah, I think that is really kind of two-stage. The first one is planning and second one is operation. So during planning stage, normally day ahead, you have all the generation, demand, network information, and then you may be able to train the neural network. And during the operational stage, really day ahead, then real time, then you can use the trained model to kind of have a quick assessment in milliseconds. Yeah, really good idea. Thank you very much. Cheers.
Thank you, Jim. Thanks.
Okay, I see here we have a new questions from Robin, but I would like first to give the chance to other attendees, and then I will leave the room for Robin to discuss with Panos in more detail. So I will now call the Chan Sing Lai to ask or to read this question.
Yeah, thank you. Thank you, Panos, for this sharing with us the interesting work. So I have a question about the training of the model. So as we may aware that there are significantly more data for training the model, which they are from the normal cases. So when the system operates normally, functioning well. And I would assume that very less or least cases where the fault or even instability happens for the system. So if you use the data like this to train the model, then it's likely that you will see the model giving a lot of cases where it's not detecting any issues with the system, and majority of the case, this might be true. So it gives you a very nice kind of result as well. So my question is, have you considered the question about data imbalance for your problem at the moment? Thank you.
Thanks a lot, Toon. I think that's a quite good question. The unbalanced class problem is a challenge, is a big challenge. When you are dealing with, when you are training using simulated data, you do have some control of the generation of the data set, right? So you can make sure that it's a challenge, it's not easy to do, it's a task on its own, but you can have control over what cases you are feeding as a training in a machine learning model. So if we are talking about real world measured responses to train a model, that's a huge problem, I would say, because these events are quite rare. So to find real data to train such a model would probably be very hard to do, or you would have to wait a very, very long time to get this data. So in terms of when we do have the simulation data, still it's hugely unbalanced. So we had, from these 45,000 cases, we had only 7,000 roughly usable cases that produced some kind of a cascade, so produced at least one activation of a protection device. There are specific methods that you can use to address this problem, but at the moment we haven't tried particular methods to work with this unbalanced problem. But what we did is we paid extra attention to the recall that I mentioned in the end, which is one metric that would particularly look at so both recall and precision actually would tell you where the model is failing. So as you said, accuracy can be a bit quite misleading, because one case was the convolutional, I think, autoencoder would keep on saying everything is fine. So in every single case would say everything is fine because this was the most common class, and this had a kind of okay-ish accuracy on that matter. So the only thing we did is we tried to balance the training data set. So we provided an even number of no cascade and an even number of cascade happening. So from these 45,000 cases, we didn't use all of them. We used only some of them that caused cascades and an equal number that didn't cause cascades. In this way, you kind of alleviate a little bit this problem.
Okay, thank you, Panos. Thanks.
We have another question from Matt Deakin. I will call Matt to read his question.
Yeah, thank you, Panos, for the very interesting presentation. I was wondering if you could just tell us a bit more about the sort of tuning and the feature selection and how that compared with the different methods, particularly in this very time-constrained environment, and how that sort of worked. Because in my experience, when I've done bits and pieces, if it takes longer than a couple of seconds, it becomes really boring and you have to put it on this sort of for loop and you leave it and then you come back, but you can't sort of interact with it. Whereas I haven't done logistic regression, but my understanding is that's pretty quick, and I assume the others are slow. So how much is how much do you think the results that you got is just a function of that sort of tweakability that meant that the people could online sort of pick out the really effective bits of information, if you like?
Thanks a lot, Matt. Yeah, I think that's the truth of it, as you said. So it didn't take a huge amount of time for the training. I think quoted number is probably half an hour, the longest it took. But this was on kind of a cluster PC node that was provided by the Turing Institute. So it was on GPUs, so at least GPUs were used that, if I understand correctly, significantly increases the speed time of training. So having said that, 2 weeks was by no means, it wasn't enough to do proper tuning of hyperparameters and feature selection. So feature selection was done only after the training using permutation. So we didn't try to go back and reduce the features and retrain the network to see how it performs, which is the next step. But you're correct to say that 2 weeks was not enough for that. It was quite restricted. Yeah, I think, does that answer your question?
Yes, yeah, that's very useful. Thank you.
A new question arises from Evelyn Halen. So Evelyn, can you please read this question? Evelyn, are you with us?
She's just dropped a comment to say she can't unmute. So if you could read the question.
Okay, great. Sorry for that. So the question is, given the small number of accuracies of cascading events, what is the uncertainty of the predictions? And if there is substantial uncertainty, how can you deal with this uncertainty in operation?
Yeah, I think this is related to a previous question as well, that I think this is a problem on its own. This is the problem I tried to mention. How do you sample that, or how do you generate the training data set? So effectively, this inherently includes how do you make sure that you capture as many cases as you can to train the model with. So again, I would probably try to address this at in the same way. you can use, because we use simulations for training, so you can use techniques to bias the simulations towards getting more meaningful points to include in your data set. Robin is probably the person to ask what methods to use about importance sampling or efficient sampling and so on. We didn't try anything like that as part of this project. We just did a brute force approach. So we discretized the different operating conditions and we just simulated everything. And because the network was quite small, it was a 39 bus network, so it wasn't huge. And the number of cases was manageable. So we, as part of this challenge, we didn't address the specific issue of how do you actually make sure that you include meaningful information in your training data set. We tried to focus on the, can you really predict it? Assuming you have a data set, can you really predict the cascade? So that is, I would say, an open question to be addressed in the future, with importance sampling playing a key role towards that direction.
Okay, thanks, Panos. Another interesting questions are from Marcos Santos. So Marcos, are you willing to read your questions?
Yes, can you hear me? Well,
yes.
Yep.
Right. So great presentation, Panos. Thank you so much. So I have a couple of questions regarding the feature selection and input selection. So for the feature selection, it seems that you have done that based on the post-evaluation of the LSTM accuracy. And based on that, have you tried to do the calculation before, like to have some sort of model analysis to help you to identify what are the best feature selections, since you are based on a simulation for the construction of the training data?
That is a very good idea, and it is a plan to do this more formally, but there was no time, unfortunately, as part of this project to do proper feature analysis. So we only did the permutation, as I explained, for LSTM and logistic regression for these two models, and we just, we didn't even retrain the models to see whether, how that would affect the accuracy in the end. So yeah, short answer is no, we didn't try any fancier feature selection, but we should.
Okay. Sorry, I forgot the second question. So the second question is about input selection. So are they based on the pre-fault conditions?
Right, so the window is actually, what we chose here is right after the fault is cleared, so the line is stripped, and at least leave room half a second before the first cascade happens. So that's how it is selected. It's not, it doesn't include pre-fault conditions, but when I mentioned future work, this is one of the things that we want to investigate further. So the actual selection of the window. So including pre-fault conditions might be useful. During fault, probably you will get some meaningful information as well. But yeah, we chose to just do a standard case of after the fault is clear, after the line is stripped, and then take a chunk of data basically after that.
All right, thank you so much.
Okay, thank you, Panos. So I see that Robin is really interested in this topic, and I will now leave you to discuss about this and to ask the rest of your questions, and be aware that we are running out of time. We have five more minutes.
Hi. Okay, I'll try and go quick. So I think Matt asked about the hyperparameter stuff that I was wondering anyway. I was just wondering, I guess the most interesting one for me is, can you use these to make causal links between events or parameter values and what's leading to the cascade, or is it essentially a kind of completely black box? Box says cascade's coming or cascade's not coming, but you can't actually use it to tell you why.
It's, yeah, my understanding is that it's probably a black, so logistic regression is not so much of a black box. So you could get information from logistic regression by looking at the weights, because it's quite straightforward way how it multiplies with the with one of the inputs basically. But the other ones are probably black box. However, I do see advances. I think the terminology is interpretability of machine learning or neural networks. So there are techniques that you can, I don't know how they work, to be honest. I haven't used them. We haven't used this as part of this project, but I think it would be something interesting to look at rather than just have a black box telling you this is happening because of that. And
yeah, I mean,
decision,
I guess
yeah.
if the people from Turing are probably, I don't know, quite happy to have
Sure.
like data-driven stuff, but when you then get a an engineer who's been working at National Grid for a while, they might want a little bit more of a kind of meaning, especially around the area of cascades, where the kind of the impact of a decision that's made or not made is really quite significant. So yeah, I don't know, I was just wondering.
Absolutely, yeah. I mean, I think this is the main motivation behind the use of decision trees in the first instance. So the first time people applied machine learning methods to such a problem, they use decision trees because they're actually readable. You can see fully why the decision is made. So that was the thinking behind that. So the more complicated models you get, how I have it in my mind, my understanding is that you get better performance, but you lose in how much you understand from the model itself, but you increase the accuracy. So seeing that even logistic regression performed quite well, maybe you can say, well, let's go with that one. Maybe we have maybe a bit less accuracy, but you can understand what it does. So you have this array of choices effectively to do.
Yeah, it's really interesting. I guess I'll just ask my very last one, which is just, did you just use kind of real-time measurable inputs, or did you also use some things that you might say need a dynamic state estimator for, like rotor angles, stuff like that?
Yeah, so I briefly touched on that. So the results I presented, the results I presented are actually do include some state variables that wouldn't normally be measured by PMU. So speed of a machine, for example, rotor angles as well. But after the data study group finished, we tried the similar setting with only PMU measurable quantities, again, under the assumption that you have a PMU at every single node of the network. So all the buses, all the lines are measured. And we kind of got similar performance, so it didn't really make a huge difference.
Okay, that's really promising. Cool. I'll be quiet now because I think they're trying to.
Okay, we are out of time. I would like to close the discussion. Thank you very much for attending webinar series, and a special thanks to Panos for contributing with his speech today. So all the best and enjoy the rest of your day. Goodbye.
Thank you very much. Thank you, Dragan. Thank you, everyone. Bye.
Bye-bye.